Good morning, welcome back. In the previous two videos, we introduced the ER modeling and the enhanced ER modeling. In this video, we will look at normal forms and use normal forms to normalize relations to reduce redundancy and improve database quality. So let's move to this section 3.5 on normalization. Now, to see the problem we have from our design, so we use the ER model and enhanced ER model. We designed the database, and this is the table and student table. So let's look at the student table. We have social security number, last name, middle name, initial, first name, phone, email, birth date, street, city, state, and zip code. Now we're going to see a lot of redundancy here is in the, you can see this is right here, and we have the city, Savannah. Now the state is the same, and here, and you can see that's the problem here, and also here, if you have a zip code, and you must have the same city and same state. So here, the student table stores city and state redundantly and for the same zip code. In this section, we're going to introduce normalization. And this is the process that decomposes the relations with redundancy into smaller relations that satisfy certain properties. These properties are characterized into normal forms. A relation is said to be in a normal form if it satisfies the properties defined by the normal form. Four commonly used normal forms are introduced in this section: first normal form, second normal form, third normal form, and Boyce Codd normal form and BC normal form. Each normal form ensures that a relation has certain quality characteristics. Normal forms are defined using functional dependency. So let's look at functional dependencies now. So the problem in the student table in figure 3.22, so this is 3.22, is that city and state are determined by zip code. This can be characterized using functional dependency. So we're going to define functional dependency using this notation, mathematical notation: X determines Y. So that means, and if this is X, it's a set of the attributes, and Y is a set of attributes. So what does that mean? If these two tuples have the same value on X, and then they're going to have same value on Y. So this is the functional dependency. So for example, here, you have a zip code determines city and state. since for every two tuples with the same zip code, their city and state values are the same. So please note that a functional dependency in a relation must be valid for all the instances of the relation at any time. And once a functional dependency is specified, you need to make sure that the dependency is not violated at any time. The database management system can enforce the primary key, foreign key, and domain constraints, but it cannot enforce functional constraints. You can write triggers to enforce functional dependencies. So we're going to look at the triggers in the appendix G. So we're going to look at the database triggers. So here are some inference rules for functional dependencies. Given a set of functional dependencies, you can derive new functional dependencies using the following inference rules. Reflexivity rule. So if X here is means contain Y, then X determines Y. So that's very obvious. Argumentation rule. If X determines Y and then XZ determines YZ. So because X determines Y. So you can add the same thing on both sides. Union rule. If X determines Y and X determines Z, then X determines YZ. Decomposition rule. If X determines YZ, then X determines Y and X determines Z. Transitivity rule. If X determines Y and Y determines Z, then X determines Z. Pseudo transitivity rule. If X determines Y and WY determines Z, then WX determines Z. These rules are intuitive and easy to prove. So here, see the example of the proof of the reflexivity rule and the pseudo transitivity rule. So you can prove the union rule and you can prove and the pseudo transitivity rule. So this is all very simple and easy. All right, so let's look at another concept here. It's called minimum covers. There are many functional dependencies in a relation. For example, in the student table, in the previous figure for the student 3.22, you may identify the following functional dependencies. So here's social security number determines last name, middle name, initial, and first name, and social security number determines zip code, determines phone and email. So a lot of this. Some of the functional dependencies, such as social security number determines social security number and last name determines last name, these are trivial, and some can be derived from the others using the inference rules. A functional dependency, X determines Y, is trivial if both sides contain common attributes. So they're common attributes. So now we define the minimum cover. Minimum cover is a set of functional dependencies F that satisfy the following conditions. Every dependency has a single attribute for its right-hand side. For every dependency, X determines A, there is no dependency Y determines A for this. Y is a subset of X. So that's minimal. Otherwise, you can just reduce to a smaller set. No dependency in F can be derived from the other dependencies in F. So this is the minimum cover. Now, for example, the following is the minimum cover for student table. So this is the minimum cover, minimal for everything. So there's nothing redundant. If you remove one, and so you miss something, and you cannot further reduce it. So this is the minimum cover and for the functional dependencies. Next, let's see this finding keys using functional dependencies. Typically, database designers first identify a set of functional dependencies from the semantics of the attributes in a relation. Additional functional dependencies can be derived using the inference rules. You can now define superkey and candidate keys using the functional dependencies. So now we have introduced these terms before. So now let's define it in the context of the functional dependency. What is a superkey? A superkey is a set of attributes that determines all attributes in the relation. A candidate key is a superkey such that no proper subset of it is another superkey. An attribute is called a key attribute if it belongs to a candidate key. A set of attributes X may determine many attributes in a relation. The closure of a set of attributes denoted by X plus is the set of the attributes determined by X. If X is a superkey, then X plus contains all attributes in the relation. You can use the inference rule to find all candidate keys in a relation. So for example, let R be a relation schema with attributes A, B, C, D, E, F, and G. So here's A determines CD, and B determines EF, and E determines G. Is a set of functional dependencies in the relation R. To find a candidate key is to find a minimum set of attributes K such that K determines the entire relation. You only need to consider the attributes on the left hand side of the functional dependency expression, because only those attributes can be key attributes. So here's the process. So here consider A. A determines A itself and ACD, and B determines EF. So B determines B, E, and Y is G. So because E determines G, so B and E determines EG. Now consider combining A, B. So you're going to have everything. So AB is candidate key. Now consider combining AE. So now you miss B. So this is not. And consider BE, combining B with E. So that's not enough. So here, AB is the only candidate key. All right, so now we can look at the normal forms. So we're going to define the first normal form. It's really simple definition for the first normal form. If every attribute value in the relation is atomic, this relation is in first normal form. By definition, a relation is already in first normal form. So because there's no multi-valued attributes, there's no composite attributes. So in the table, so every cell in the table is a atomic value. It cannot be further decomposed. Suppose you mistakenly put the course title as an attribute in the enrollment relationship. So here, enrollment relationship, look at this. So here, student take this course. All right, you have this enrollment student. So here, social security number and course ID. So here for the course and date registered and the grade and title right here. So here's the course title. Okay, and just by mistake. All right, it should not be here. So so now you're gonna see the problem here. So we're gonna have this. So we're gonna look at the second normal form. So there's a redundancy here. So we're gonna eliminate it and using the second normal form. What is second normal form? A relation is in the second normal form if it is in first normal form and no non-key attribute is partially dependent on any candidate key. So there's no non-key attribute is partially dependent on the candidate key. An attribute A is partially dependent on a set of attribute X if there exists an attribute B in X such that you remove this B from X, you still can determine A. So that means A is partially dependent on X. So this is what happens here is you're going to have this is a partial dependency. So if you have this is the your table here, enrollment. And so here is this candidate key. It's a social security number and course ID. And now it determines title, right? Determines everything. So this is the determines title, but title is only partially dependent on the whole thing. It just, you don't need social security number, just course ID determines title. So there's a partial dependency. So this is not in the second normal form. So we need to break it and decompose it and into, and there's two relations. So they're now becoming in the second normal form. So now you see, oh, there's no need for this this one because it's already in the course table. So that's called decomposition, and you can decompose into two. So when you decompose it, and so here is, and you're going to try to maintain the functional dependencies. So this is decomposed into two tables. So here's the enrollment table here. It's going to be this one table here consisting this 4 attributes, and there's another one consisting just course ID and title. So that's right here. And this is decomposed. Now, there's a concept of lossless decomposition. A decomposition is called lossless if no information is lost in the process. Specifically, assume a relation R is decomposed into relation R1, R2, and Rk. The decomposition is lossless if and only if, so you have this is the relation here, and you're going to have all this R1, R2, and performing this natural join together, it's the same as the original one, so there's nothing to lose. So this through the join. All right, so that's second normal form is there's no partial dependency. And now we're going to look at the third normal form. Third normal form is this. A relation is in the third normal form if it is already in the second normal form. And no non-key attribute is transitively dependent on any candidate key. And attribute A is transitively dependent on a set of attribute X. If there is a set of attribute Z that is not a subset of any candidate key, and X determines Z, and Z determines A. So that's A is transitively dependent on X. So let's look at this example. The student relation is not in third normal form because city and state are transitively dependent on the candidate key social security number. So since social security number determines zip code and zip code determines state and city. So that's city and state are transitively dependent on social security number. Now we need to normalize it and to decompose the student table and into third normal forms. So you need to remove the non-key attribute that are transitively dependent on the candidate key from the relation and place them along with their determinants into a new relation. So here we're going to have a zip code. And so in the student table, so you don't have the city and state anymore. So this is the new one. So that's the third normal form. And the relation does not have any non-key attribute and transitively dependent on the candidate key. Finally, let's look at another normal form, it's the highest here. A relation is in the third normal form, may still face some redundancy problems. So for example, this is the table, store address table. In this one, here we actually have attributes street, city, state, and zip code. And store and the store. So here, here's Kroger. So this is the on different location here. All right. All right, so we have this, and we have functional dependency here. Zip code determines a city and state, and street, city, state, and determines zip code. So do you see this? And this store address is in third normal form because this store, zip code, street, and store, street, city, state, these are the candidate keys. And every attribute in this store address is a key attribute. So there's no non-key attribute. But there's still redundancy. So if you look at this table, you're going to see a city, state information are redundant. So if you have a zip code, you have the same city and state, and zip code is the same. So you have the same city and state. So as a consequence, the store address relation suffers insertion, deletion, and update problems, because when you do this update, so if you want to do update to the zip code, you have to update all the city and state information as well. So this is very costly operation here. So it suffers redundancy problem, and have this all these issues with the data storage and performance. What do we do is now we're going to introduce a new normal form to tackle this problem. The new normal form is called the BC normal form. It's a Boyce-Codd normal form. So if a relation is in BC normal form, it is it is already in the third normal form. And further, if the determinant of every non-trivial functional dependency is a candidate key. In this, the store address relation is not in BC normal form, because here you have zip code is a determinant, but zip code here determines city and state, and zip code is not a candidate key alone. So you can decompose it into two relations: store, you have store, street, zip code, and zip code. So with this decomposition, both new relations are in BC normal form. All right, I want to put a note here is on the normal forms. So you know what is normal form? Normal form is like a measurement standard. And you see this relation in this normal form, we know this relation possesses some good properties. And normal forms are for measuring the quality of database design. Normalization is a guideline, not a mandate. And normalization reduces redundancy, but it slows down the performance because you have to perform a natural join to obtain information that is now in two or more tables. So there's a trade-off. There's still you gain some performance and you also lose some performance here. Suppose your application needs to print student mailing address frequently. If city and state are in the zip code table, and you have to frequently perform natural join operation to obtain student name and address from the student table and the zip code table, join them together. To improve the performance, you may combine zip code table into the student table. Another note here, I put it here, is normalization has been thoroughly studied in the literature. Many other normal forms were actually proposed too. These normal forms have theoretical interest, and however, what we have here, first normal form, second normal form, third normal form, and BC normal form are the ones used in the practice. There are many interesting topics that could be covered in a database text, and the focus of this writing here is on practical aspects of database systems, not the survey of normalization theory. So now, with all this background, with functional dependencies and normal forms, and we are going to look at example. So here is we're going to apply normalization into this table. So here, suppose we have this table R. So this we have attributes, faculty advisor, rank, status, student advisee, since. So this is when becoming advisee. So this shows an instance of relation right here. Now we need to identify all these functional dependencies, and from the meaning of this table semantics, we're going to draw the functional dependency. So each faculty has a unique rank. So this faculty advisor determines rank. A faculty status is determined by the rank. So rank determines the status. The attribute since records the date when a student is assigned to a faculty advisor. So faculty advisor, student advisee, and determines since. All right, so this is all the functional dependency. From all this functional dependency, we're going to get the candidate keys. So we'll get the candidate key. All right, so this is the candidate key. Is faculty advisor and student advisee. Since rank is a non-key attribute that is partially dependent on the key of faculty advisor. So this is not in the second normal form. So we're going to decompose it into R1 and R2. So now, all right, so now let's look at this in R1. Faculty advisor is the key. In R1 is not in third normal form because status this non-key attribute is transitively dependent on faculty advisors. Status is dependent on rank, and rank is dependent on faculty advisor. So R1 can be now further decomposed into R11 with faculty advisor and rank, and then R12 and rank status. So that's one example. And here is another example at 3.2. So we're going to look at 3.2. It's the same process. I want you to look at this process here. Is we have this relation R, and it consists of attributes student, course, teacher, and office. So right here. Now, the semantic meaning of this relation is as follows. A student takes a course taught by a teacher. All right, so that you have a student take a course determines teacher. A teacher teaches only one course, so teacher determines course. Teacher has an office, so this is all the functional dependencies. And now from the functional dependencies, we find out the candidate keys are student course and student teacher. So this. Since office is a non-key attribute, it's partially dependent on the candidate key student teacher. And this relation is not in the second normal form. So we're going to decompose it and into R1 and student course teacher, and R2 and teacher office. And the functional dependency in R1 are this. And now R1 is not in the BC normal form because teacher is a determinant, but it's not a candidate key. So should R1 be further decomposed? It's not good to decompose it because the semantic meaning would be lost if it's decomposed. So it's practical consideration too, and we don't go further. All right, so there's more to look at it. Here's an example, 3.3. So 3.4, so please look at this 3.5, and that is all. And for this video on functional dependencies, minimum cover, super keys, candidate keys, and the normalization, and decompose the relation to satisfy a normalization. So all this, and please look at everything and look the my writings in detail. So these are all the review questions and the exercises. Thank you for watching. See you on the next video.